Section 1 Introduction. We're delving into the world of retrieval augmented language models, which perform impressively, but their excellence comes with computational demands. These models rely on the processing of retrieved passages, which can be a taxing task. Various techniques such as conditional computation, reranking, and memory have been employed to alleviate this computational burden. Reranking is an approach where we streamline the quality of the retrieved content to reduce the quantity of passages for processing. However, the catch here is that neural reranking isn't cheap, as each retrieved candidate must be processed by a neural network. An alternative solution, known as late interaction rerankers, utilizes pre-calculated intermediate token representations and uses a smaller neural model for on-the-spot combination of the query and document representations to score the rank. This method significantly boosts speed but comes at the cost of storage and pre-computation overhead. Recently, we've seen the late interaction concept being applied to retrieval augmented generation. It tactfully balances between memory and retrieval augmentation to strike an optimal quality compute trade-off. We're introducing Glimmer, our generalized late interaction memory reranker. This is a late interaction model that unites reranking and memory in a single, comprehensive model. Much like its predecessors, Glimmer includes a memory encoder that generates pre-calculated token representations for retrieval documents, and a live encoder that merges these representations with the query. After processing the initial layers of the live encoder, a ranking layer comes into play, selecting the most pertinent passages for further processing. The model is designed to rank passages based on their usefulness to the reader, with an auxiliary loss termed as perplexity distillation guiding the process. Glimmer stands apart by utilizing a general memory and live encoder for all tasks. It's trained with multitask fine-tuning over knowledge-intensive datasets, enhancing its flexibility. We have tested Glimmer on the KILT benchmark of knowledge-intensive tasks and found that multitask training substantially enhances the model's quality compared to single-task training, particularly when we dedicate less capacity to the live encoder. Moreover, Glimmer not only outperforms other multitask-trained models and the fully invisible decoder, FID, in both quality and speed, but also successfully consolidates reranking and memory into a single efficient, high-quality model. In conclusion, Glimmer is our proposed solution for the computational demands of retrieval augmented language models, offering an efficient, high-quality unified model for reranking and memory. Section Summary. Retrieval augmented language models are computationally expensive due to the need to process retrieved passages. Reranking improves retrieval quality and reduces the number of passages that need to be processed, but neural reranking is expensive. Glimmer is a late interaction approach that unifies reranking and memory into a single end-to-end model, improving on previous methods by using a single general memory and live encoder over all tasks, trained with multitask fine-tuning over knowledge-intensive datasets. Section 2 Background. Our focus lies in striking an optimal balance between the quality of our results and the computational resources required for inference. The following segment outlines the methods of fusion in decoder, FID, and Glimmer, both of which our approach is based upon, and highlights their computational characteristics. For a more detailed study of these methods, please refer to the relevant literature. FID is derived from a model known as T5, which operates on an encoder-decoder structure. The process begins by identifying multiple relevant textual segments for each input. These segments are then coupled with the input, forming a series of input text pairs. Each pair is separately processed by the encoder, resulting in a stream of encoded pairs. These are then merged into a singular sequence of token representations, which is interpreted by the decoder to generate the intended output. Live components of each model are depicted in blue, while pre-inference, pre-computed elements are illustrated in orange. Let's discuss the mathematical representation of the above process, using simpler language. We will denote by K, the number of text passages, n_p, the number of tokens per passage, n_t, the total number of target tokens, L, the number of layers in the model, and D, as the dimension of the model. According to previously performed analyses, the floating point operations per second, flops, needed for a single inference sample of FID, disregarding the computation of attention scores, is given by the total flops, f_FID, is made up of two primary components, the encoder and cross-attention, and the decoder. For the encoder and cross-attention part, it's K times n_p times L times 14 times D squared. For the decoder part, it's n_t times L times 14 times D squared. Each token from the feed-forward layers contributes 8 times D squared to this total. Each self-attention projection layer contributes 4 times D squared, and each cross-attention projection layer adds 2 times D squared. For a more detailed breakdown of the FID model's computational complexity, please refer to the provided literature. Section Summary. The section describes the fusion in decoder, FID, model, which is based on a T5 encoder-decoder model. FID retrieves relevant text passages, encodes them separately, concatenates them, and attends to them to produce a target output. The flops for a single inference sample of FID is given by a formula that includes factors such as the number of passages, tokens per passage, layers, and dimension of the model. Section 2.2 Lumen. We aim to reduce the computational cost that occurs when processing large passages of text, an aspect that becomes particularly crucial during the encoding phase. To achieve this, we present an approach that takes advantage of pre-computation to alleviate this burden. In our approach, rather than retrieving the raw text during inference, we recover intermediate layer representations, which were computed beforehand. Our model is essentially an adaptation of the pre-trained T5 encoder-decoder model. The primary variation is in the division of the encoder into two distinct parts, a large, memory encoder, and a smaller, live encoder. The memory encoder, which consists of the first portion of layers up to the fraction 1 alpha, works offline to generate memory representations from passages in our corpus. Then, the smaller live encoder, composed of the remaining alpha fraction of layers, updates these pre-computed memory representations based on the specific input and task at hand. To ensure compatibility between these pre-computed memory representations and the actual input, we use the memory encoder to process the input before combining it with the memory representation. This operation can be represented in a simplified way. We concatenate the memory-encoded question with the memory-encoded passage for each I, to create a composite representation denoted by H_I. Then, to generate the final output, the decoder takes a sequence of live encoded versions of these composite representations, H_1 through H_k, and the original question. The parameter alpha plays a critical role here. Choosing alpha as 1 makes our model resemble the standard fusion in decoder, FID, model, while choosing alpha as 0 makes our model fully rely on the memory. The inference computational cost is reduced as the live encoder operates on only alpha proportion of the layers, which amounts to alpha fraction of the computational complexity compared to the standard FID reader for a given model size. The total computational cost of our model can be calculated as the sum of the following components: the cost for the encoder, dependent on alpha, model size, and other parameters, the cost for cross-attention, and the cost for the decoder. The computational cost for each component can be represented as multiplications of related parameters, which we will not go into in depth here. Section Summary. The majority of flops in the encoder are consumed by processing retrieved passages, so the paper proposes a method to reduce the encoder inference cost by pre-computing the encoder representation for retrieved passages. This is done by initializing a T5 encoder-decoder model and dividing the T5 encoder into a memory encoder and a live encoder, which are applied offline to passages in the corpus and updated on the fly by the fine-tuned live encoder. Section 3 Glimmer. We're introducing Glimmer, a system that improves on previous models with two significant changes. Firstly, it includes a built-in reranker, and secondly, it shares the memory and live encoder across multiple tasks. Let's explain what this means. Reranking, or ordering potential answers based on their relevance, can be challenging. Smaller models may not be powerful enough to accurately judge relevance, while larger models are expensive and negate some of the benefits of reranking. However, Glimmer navigates this dilemma by pre-computing the majority of passage representations. Furthermore, Glimmer leverages the early layers of the live encoder for reranking. This provides us with a strong reranking model without significantly increasing computational cost. Sharing the model's weights across tasks also lets us train the memory encoder without storing duplicate pre-computations, enhancing the effectiveness of the live encoder. Now, let's take a deeper look at Glimmer's architecture. It splits the live encoder into two components. The first component is responsible for the initial interaction and reranking, while the second component further processes the representations of selected passages. A portion of the live encoder's layers, represented by beta, is in the first component. The remainder is in the second component. After the first live encoder, a linear projection layer is applied to the first token of each input passage pair to generate a score reflecting the relevance of the passage. Out of the initial set of passages, the top M passages with the highest scores are processed by the second live encoder. The rest are discarded. The output of this second live encoder is then fed to the decoder, similar to previous models like FID. The model's equations, displayed in the original text in LaTeX format, illustrate the computational processes involved. They demonstrate how the memory encoder is applied to the query and each passage, how these are processed by the live encoder A, and how scores are assigned to the passages. Based on these scores, the model selects the top passages, processes them with the live encoder B, and passes the results to the decoder. This entire process simplifies the task and increases the effectiveness of the live encoder. Section summary. The Glimmer architecture incorporates a built-in reranker and shares the memory and live encoder across many tasks. By reusing the initial layers of the live encoder for reranking, Glimmer yields a powerful reranking model at relatively modest computational cost. The architecture divides the live encoder into two components, where the first component is responsible for initial interaction and reranking and the second component performs further processing on representations of selected passages. Section 3.2 Training. In Section 3.2, we discuss the training process of our model, focusing on the memory encoder, live encoder components, the scoring projection, and the decoder. Unlike previous models, our training process involves every part of our model simultaneously, and we don't need to freeze or stop updating the memory encoder while training. This is possible because we use a single memory encoder across all tasks. Our training process uses a unique technique called perplexity distillation. This technique pushes our model to rank different passages based on how much they reduce the perplexity, a measure of how well the model understands the text when they are used alone as input to the decoder. To explain this more simply, imagine each passage as a potential answer to a question. Our model assigns a score to each passage based on how well it thinks that passage answers the question. The higher the score, the better the model thinks that passage would serve as an answer. Now, to calculate these scores, we need two components. First, we need the rank score, which ranks passages based on how much they reduce perplexity. We calculate this score by applying a formula that compares the passage score and a normalization constant over all passages. The second component is the language model score. This score is calculated based on how well each passage, when considered as a response to a given query, is predicted by the language model. Just like the rank score, this score is calculated by comparing the likelihood of each passage being the answer over all possible answers. The loss function used in training is the KL divergence, a measure of how one probability distribution is different from a second, reference probability distribution. We use it to minimize the difference between the rank score distribution and the language model score distribution. In simpler terms, our model's objective during training is to make sure that the scores it assigns to different passages based on their potential to reduce perplexity, rank scores, matches the scores it assigns based on the language model's prediction, language model scores. By doing this, our model becomes better at identifying the best passages for answering a given question. Section summary. The memory encoder, live encoder components, scoring projection, and decoder are all trained together using an auxiliary perplexity distillation loss. This loss helps the model rank passages based on how much they lower the perplexity of the final generation, minimizing the KL divergence between the distribution implied by the reranking scores and the distribution implied by the resulting perplexities. Unlike in previous methods, the memory encoder does not need to be frozen as a single memory encoder is shared between all tasks. Section 3.3 Computational Analysis. We're now moving on to Section 3.3, where we delve into a computational analysis. When comparing the Glimmer model to the model, it becomes apparent that the disparity in their computational complexity largely comes down to how they handle reranking. To paint a clearer picture, let's imagine we have chosen M passages to process. These passages are processed by the full live encoder and are then passed through the decoder in both models. This process has the same computational cost as if the model was applied to M passages. This is a smaller cost compared to processing all the originally retrieved passages, let's say K passages. However, here's where Glimmer has a bit of a twist. Even for those passages that weren't chosen for processing, Glimmer applies the first live encoder component. This additional step incurs a reranking cost. If we simplify the reranking cost equation, it involves factors such as the difference between the total number of retrieved passages, K, and the selected ones, M, the number of layers we choose for reranking, represented by the fraction beta, the passage length, represented by alpha L, and the square of the hidden dimension size, d squared, all multiplied by a constant factor 12. But here's the catch. If we use a smaller number of selected passages, where M is much less than K, and a smaller fraction of reranking layers, where beta is much less than 1, the Glimmer model can be a lot less computationally demanding than the model when dealing with K retrievals. But it's worth noting that our computational analysis here is just taking into account the number of floating point operations, flops. We're not factoring in practical latency, which can often be more impactful. Particularly for autoregressive inference, the decoding process can be slowed down more by memory bandwidth constraints than by flops. There's a silver lining though. Many contemporary techniques have been developed to help ease this constraint, such as variants of multi-query attention, layer sparsity, speculative decoding, among others. When a model needs to operate in a scenario where inference speed is crucial, these techniques are likely to be utilized to make flops the primary constraint. For the purpose of this paper, we're going to stick to measuring computational cost in terms of flops. We will present a separate analysis on how flops and latency interact with the model later on. What you'll see as we proceed is that the Glimmer model offers a more favorable balance between computational efficiency and quality of results when compared to both the model and the FID model. Section Summary. The computational complexity of Glimmer and FID differs in reranking. Glimmer processes a smaller number of selected passages, resulting in significantly less computational intensity than FID with K retrievals. However, this analysis is limited to flops and not practical latency, which can be improved with recent techniques such as multi-query attention and layer sparsity. Glimmer represents a better quality compute trade-off than FID. Section 4 Experiments. We conducted several experiments for this study, utilizing a model called Glimmer. This model is based on the architecture known as T5.1.1. It was developed using JAX, FLAX, and FlaxFormer, which are widely known programming tools. Our models were initialized from publicly available T5.1.1 checkpoints. We fine-tuned another model known as FID following the guidelines provided in its original paper. To better understand how we adapted these models, it's important to introduce a term we used, alpha. Alpha is a proportion of live layers in our model. We used these live layers to initialize our memory encoder and live encoder, which are crucial parts of the Glimmer model. Specifically, we took the first 1-alpha proportion of layers from the T5 encoder to initialize the memory encoder. We then used the remaining alpha proportion of layers to initialize the live encoder. For the main experiments, alpha was set to 1/3. For the fine-tuning phase, we used an optimizer known as Adafactor with a constant learning rate of 0.0001. This phase involves adjusting the model parameters to improve performance. We maintained a batch size of 128 and a dropout rate of 0.1 for all tasks, meaning 10% of the inputs were randomly excluded each time the model was updated to prevent overfitting. When conducting multi-task training, we selected tasks randomly and uniformly. We set aside 48 tokens for the question and 304 tokens for each passage in our model. Apart from the standard language modeling loss, in our reranking experiments, we applied an additional distillation loss based on perplexity, a measure of how well the model understands the text. The weight and temperature of this loss were both set to 1.0. Our training continued until the model performance stopped improving. We then chose the checkpoint that showed the highest performance on the dev set, a subset of the data not used in training. Lastly, for making predictions, we used a technique called greedy decoding, which at each step selects the most probable token or word. Section Summary. The experiments involved using the T5.1.1 architecture implemented in JAX, FLAX, and FlaxFormer, with models initialized from public T5.1.1 checkpoints. The memory encoder and live encoder were initialized with different proportions of layers from the T5 encoder, with the main experiments using alpha equals 1/3. Fine-tuning was done using the Adafactor optimizer with a constant learning rate of 0.0001, batch size 128, and dropout rate 0.1 for all tasks, and an auxiliary perplexity distillation loss was used for reranking experiments. The models were trained until convergence and the checkpoint with the highest performance on the dev set was selected for inference using greedy decoding. Section Data. We train and evaluate our models using a selection of datasets from the KILT benchmark, which is known for its emphasis on knowledge-intensive tasks. Specifically, we utilize question-answering datasets such as natural questions, trivia QA, and hotpot QA, a fact verification dataset called Fever, and slot-filling datasets zero-shot RE and T-Rex. To counteract the issues posed by imbalanced datasets, we implement a relevance filtering process. When it comes to data retrieval, we adopt a specific retrieval procedure. We break down Wikipedia into sections of up to 200 words each, and select those passages that most closely match the query, as determined by a pre-trained GTR base model. Looking at our key findings, we draw comparisons between FID, an updated architecture model with multitask training, and Glimmer. Glimmer's inherent re-ranking mechanism allows it to process passages more efficiently, thereby enabling it to retrieve more documents compared to FID. As illustrated in the figure, this increased efficiency results in a better performing and quicker model. As a result, Glimmer outperforms both FID and the other model at a faster speed. Section Summary. The authors trained and evaluated their model on a subset of datasets from the KILT benchmark, including natural questions, trivia QA, hot pot QA, fever, zero-shot re, and T-Rex. They used a relevance filtering procedure to address imbalanced datasets and a retrieval procedure to retrieve passages with the highest similarity score to the query. The main results showed that Glimmer outperformed FID in terms of efficiency and speed due to its inbuilt reranking. Section 4.3 Retrieval and Reranking. In Section 4.3, we delved into the retrieval and reranking processes of our model, Glimmer, analyzing how various options related to these processes can influence the outcomes. It's important to note that our main findings indicate that Glimmer performs better in terms of cost effectiveness compared to the FID model, mainly due to its ability to initially retrieve more passages and then fine-tune the selection to a significantly smaller set. Now, let's look at the number of passages retrieved and chosen. Our data visualization illustrates how performance is impacted by both the total count of passages retrieved and the number of passages chosen after the reranking process. Interestingly, we observe a substantial increase in performance corresponding to the total count of retrieved passages. However, this performance boost diminishes significantly as the number of selected passages increases. These observations suggest that the reranking mechanism is very effective at choosing beneficial passages. The key factor, therefore, lies in whether the relevant information was included in the initially retrieved passages. This concept is reinforced by another data visualization, which shows that applying a sufficient number of reranking layers can almost match the performance achieved when using all 25 retrievals. That being said, it is clear that some form of neural reranking with full interaction is beneficial. If the reranking proportion is less than 0.25, meaning fewer than 2 reranking layers are used, this substantially hinders performance. Interestingly, as depicted in yet another visualization, when a large number of retrievals are made, the selection process is so accurate that choosing additional passages can actually hurt performance due to unnecessary distraction from irrelevant context. The data suggests that with more reranking layers, the optimal number of selected passages is actually lower, since the highest ranked passages are better at encompassing all useful information. Section Summary. The study compares the performance of Glimmer and FID in retrieval and reranking, and finds that Glimmer achieves higher quality at lower cost by retrieving more passages initially and reranking to a smaller number of passages. The results show that performance strongly increases with the total number of retrieved passages, with sharply diminishing returns in the number of selected passages after reranking. The optimal number of selected passages is lower with more reranking layers, as the top-ranked passages better capture all useful information. Section Separate Reranker. We want to delve into the impact of utilizing the live encoder to perform reranking as opposed to employing a distinct reranker. We contrast the efficiency of our model, Glimmer, when it makes use of a separate reranker, with the reranker either initialized from T5 or trained from the ground up. We find that using a separate reranker delivers similar results, but at the cost of a more complex model, alongside increased memory and computational requirements. It's crucial to begin the reranker with pre-trained weights. If we try to build reranking layers from scratch, it noticeably decreases performance. We now shift our focus to multitask training, which is the second major enhancement in Glimmer. It facilitates the sharing of memory and live encoder between tasks, thereby leading to the training of the memory encoder. We perform several experiments aimed at understanding the effects of these improvements. One experiment, displayed in a figure, highlights the power of multitask training. It does this by comparing performance on the natural questions (NQ) dataset for models trained solely on NQ with models trained on KILT. To pinpoint the influence of multitask training, we examine FID and some other models, ensuring memory training is applied across all models in this comparison. The data shows that multitask training provides substantial benefits to all models. However, its effects are exceptionally significant for some models, particularly when the live proportions are smaller. Another figure presents a contrast between single and multitask training in relation to the live proportion. The performance of multitask training tends to stabilize earlier and has a more pronounced effect when the live proportion is smaller. The live encoder has a distinct role to play, which differs from its original pre-training task. Therefore, it makes sense that the live encoder greatly benefits from a larger and more diverse set of data. Additionally, multitask training allows for the learning of a memory encoder. We find, as demonstrated in a table, that training the memory encoder is crucial for performance. This comes as no surprise, given that the pre-trained encoder was not originally designed to function as a memory encoder. Section Summary. The paper discusses two major improvements in Glimmer, using a separate reranker and multitask training. Using a separate reranker achieves comparable performance but with additional memory and computation overhead. Multitask training significantly benefits all models, especially the live encoder, and enables learning a memory encoder, which is important for performance. Section 4.5 Other ablations. In Section 4.5 titled, Other Ablations, we explore various decisions made in the design and training process of the Glimmer architecture. A table is provided in the section, offering an ablation study, which essentially investigates the effect of individual components of our model. In the original design, the Glimmer architecture included a distinct question encoder. This was required because we didn't fine-tune the memory encoder. However, in our current iteration, we've updated the memory encoder with a process known as multitask training. Consequently, we've decided to utilize the memory encoder to also handle question encoding. This change simplifies the model by removing the need for a separate question encoder and also reduces the overall parameter count. We observe that this streamlining of our architecture does lead to a marginal decrease in performance. There are also several considerations related to the reranking process, such as determining the weight of the perplexity distillation loss, setting the temperature for the score and perplexity distributions, and choosing the method for generating a reranking score. We notice that if we assign too much or too little importance to the reranking loss, the overall performance deteriorates. On a positive note, using a lower temperature for the score and perplexity distribution seems to be beneficial. We suggest that this is because the impact of most individual passages on perplexity is usually minimal, and using a lower temperature can help accentuate these minor differences. Lastly, we find that using the first token of each passage to generate a reranking score gives us similar results as when using mean pooled representations for the same task. Section Summary. The authors present ablations of various decisions in the Glimmer architecture and training procedure, including the use of a separate question encoder and parameter choices for reranking. They update the memory encoder with multitask training, simplifying the architecture and reducing parameters, but at a small cost in performance. Lowering the temperature for the score and perplexity distributions helps distinguish differences in individual passages, and using the first token of each passage performs similarly to generating a score from mean pooled representations. Section 5 Related work. Our research investigates methods to enhance the efficiency and quality of retrieval augmented language models, a type of AI that uses additional context to improve performance. This work aims to harmonize three main areas of study: late interaction memory, late interaction reranking, and learning to retrieve. We base our model structure on a widely used retrieval augmented model known as Fusion in Decoder. Furthermore, our research utilizes a method called multitask training on a benchmark called KILT, similar to past research approaches. A crucial part of our work is the incorporation of memory. Retrieval augmentation tends to require more resources due to the extra context that the language model must process. Memory models, such as Tome and Memorizing Transformer among others, seek to lessen this resource strain. They do this by preparing and storing representations in a memory bank in advance, allowing the model to directly retrieve these instead of creating them in real time. However, a common pitfall of this approach is a potential drop in quality, as the stored representations aren't specifically conditioned for each unique input. This is where late interaction memory comes into play. It enhances memory-based methods by only partially precomputing retrieval representations. The rest of the interaction between the memory and the input happens in real time, allowing for a more tailored response to individual inputs. Our research largely follows this approach, striving for a more effective and efficient language model. Section Summary. The paper focuses on improving the quality compute trade-off for retrieval augmented language models by unifying three lines of research: late interaction memory, late interaction reranking, and learning to retrieve. The approach uses the architecture skeleton from Fusion in Decoder and employs multitask training on KILT. Memory models such as Tome and Memorizing Transformer attempt to avoid the cost of retrieval augmentation by precomputing representations and storing them into a memory, but late interaction memory improves the quality of memory approaches by partially precomputing retrieval representations and performing some interaction between memory and input on the fly. Section Reranking. The process of choosing and ordering search results, referred to as reranking, is a delicate balancing act. On one side, we have the expensive online ranking systems that engage in extensive interaction. On the other side, dual encoder methods such as DPR and GTR are more commonplace. These techniques evaluate their scores based on the degree of similarity they share with a pre-compiled collection of passage representations. Typically, various retrieval models are utilized sequentially. A less costly scoring model initiates the process, which is then succeeded by a more powerful, yet costlier reranker. Many rerankers, like Colbert, pre-TTR, SDR, and poly encoders, strike a fair balance between the quality of the ranking and its speed by incorporating a strategy known as late interaction. Glimmer integrates late interaction memory and reranking into a single model, reusing the precompiled representations for both applications. In the context of training retrieval models, they are often educated with supervised data, drawing from gold retrievals in databases like MS-Marco or TREC-CAR. When choosing which passages to retrieve for enhanced generation, we have an extra piece of information: which passages are most beneficial for the reader model. Several existing pieces of work harness this signal to better their retrieval process. In our case, we're following the approach by Atlas and using a method called perplexity distillation to train our reranker. The goal is to pick out passages that aid in reducing the complexity of understanding for the reader model. Section summary. Retrieval procedures for language models face a trade-off between expensive online ranking and cheaper dual encoder approaches. Typically, a pipeline approach is used with an initial cheap scoring model followed by a more powerful and expensive reranker. However, Glimmer combines late interaction memory and reranking into a single model, sharing the pre-computed representations for both use cases. Additionally, perplexity distillation is used to train the reranker to select passages that help lower reader model perplexity.